Let A be a real 12 by 12 matrix such that characteristic polynomial of A is equal to lambda squared plus 1 to the 6th power. The minimal polynomial of A is equal to lambda squared plus 1 to the 3rd power. And the dimension of the null space, A squared plus the identity matrix, is equal to 6. With that information, we want to find all possible rational canonical forms for A over the real numbers. Now, in our previous problem, we studied a matrix whose rational canonical form consisted of a single block. So, the focus there was on understanding companion matrices. In this problem, we want to focus on the information that tells us the number of blocks and the size of our largest block. So, with that, we have our irreducible factor over R. It's going to be Q of lambda equal to lambda squared plus 1. For the size of the largest block, we use the degree of the minimal polynomial. So that's going to be the degree of our Q times the exponent on our Q of lambda in the minimal polynomial. So that's going to be 3 times 2, or 6. So the size of our largest block is 6. Then the number of blocks is given by, take the dimension of the null space of the matrix, Q of A, we divide by the degree of Q. So in this case, we'll have 6 divided by 2, which gives me 3. So we'll have 3 blocks, the largest of which has size 6. Just a note, for our formula here, there's a parallel when we use Jordan canonical form. So if we have the same type of problem, single irreducible factor, for the number of Jordan blocks that we would use dimension of the null space. Okay, and here the irreducible factor is going to be A minus lambda I, where lambda is our eigenvalue. So in that case, we'll be taking the dimension of the eigenspace, and then the degree would just be equal to 1. So when we use Jordan form, the number of blocks is just given by the dimension of your eigenspace. Here we don't have any eigenvectors, so this is going to be the replacement. Now, our next step is to set up the blocks that can occur in our rational canonical form. These blocks are going to be companion matrices. Recall, the point of a companion matrix, somebody gives you a polynomial, you form the companion matrix for that polynomial. The minimal polynomial of the matrix will be your original polynomial. Here, our blocks are going to have minimal polynomials that are powers of our irreducible factor, lambda squared plus 1. So, if the minimal polynomial is lambda squared plus 1, we have a 2 by 2 block. If it's lambda squared plus 1 squared, we have a 4 by 4 block. If I have lambda squared plus 1 cubed, we have a 6 by 6 block. And we note we don't have any larger blocks. So we just need to figure out the companion matrices for these 3 types of minimal polynomial. Now, for size 6, the minimal polynomial is lambda squared plus 1 cubed. So how do we set up a companion matrix? We'll have 1s on the diagonal below the main diagonal. For the last column, we'll load in the coefficients of our minimal polynomial. Then we'll have 0s elsewhere. Now, if we expand lambda squared plus 1 cubed, okay, we'll have lambda to the 6 plus 3 lambda to the 4 plus 3 lambda squared plus 1. The rule for loading in the coefficients, we ignore the leading term. Then we're going to put the coefficients in, starting at the bottom, working our way up, and we put in minus signs. So here, coefficient of lambda to the 5th is 0. For lambda to the 4th, I have 3, but I put in a minus sign to give me a minus 3. Lambda cubed, I have a 0, and so on. So we'll call this companion matrix C6. Its minimal polynomial is lambda squared plus 1 cubed. For lambda squared plus 1 squared, Okay, our minimal polynomial is lambda to the fourth plus 2 lambda squared plus 1. So we'll put our 1s on the diagonal below the main diagonal, and then we start reading off coefficients, ignoring the leading term. So we'll start with a 0 for lambda cubed, then a minus 2, a 0, and then a minus 1. Call this companion matrix C4. Then for size 2, minimal polynomial is lambda squared plus 1. So I have a 1 on the diagonal below the main diagonal. Then we just have, ignoring the main term, 0 for coefficient of lambda, and then a minus 1. I'll call this block C2. Now, how many ways can we load our 3 types of companion matrices into a 12 by 12 matrix? Here, we can put our blocks in decreasing order down the diagonal. Okay, rearranging the order of the blocks is just changing the order of our basis vectors. Now, we can have a C6 and a C6, a C6, a C4, and a C2, or a C6 and 3 C2s. We note, here we have 2 blocks, here we have 4 blocks, so we can discard those possibilities, which leaves us with a single possibility. So we note in this case, we don't need to do any more work to determine which type of form it is. With the conditions that we've stated, we pin down the rational canonical form to one possibility.